Hi everyone. So today we are going to talk about optimal trade-offs for estimating polyobservables on FOCS 2024. This is a joint work with Sitan from Harvard and Qi from Tsinghua University. So to begin with, let's talk about the motivation. As a theories for quantum computer science, the primary goal is to find what can we achieve potential quantum advantage on near-term devices. Some well-known examples can be factoring, sampling, or optimization. And today we're going to talk about learning from quantum data, which is also an emerging field in quantum information science. In general, it's like you have a quantum system, and our goal is to estimate some properties through observables. And to achieve these goals, we just perform some measurements to get some classical outcomes and then make predictions on quantum system based on this classical statistics. Another motivation is to learn how the underlying physical systems works via learning from quantum data. This is a central task in quantum information, especially in quantum benchmarking and quantum certification. Roughly speaking, it's just we are trying to know what is going on the unknown quantum device. So in this talk, we're going to talk about the complexity and potential information theoretical advantage uh, for learning from quantum data. In general, learning from quantum data can be described as follows. The learner is given n copies of unknown quantum state rho, and the goal is to learn some properties of rho, say the expectation values of observables, the purity of rho, the entropy of rho. A most natural setting is the unentangled measurement, where we just have a rho and make measurements, and then we have another copy of rho and make another measurement, and so on. And this model is practical but weak, and we have to do classical data post-processing. A stronger model is entangled measurement, which we have M copy together and perform a joint measurement. It's strong but impractical. There's some model in between. A first example is bounded quantum memory, which we are going to cover later, is that you have a new fresh copy of rho, you make a measurement, and you have a k-qubit quantum memory. So after the measurement, you can store k-qubit in the quantum memory, and then you get another fresh copy of rho and you perform a joint measurement on n plus k qubits, and then you store another k qubits in the quantum memory. So in this case, you can have a very deep circuit. You can have a memory just like classical classical computers. And because we are talking about learning from quantum data, so we have adaptivities, which means that based on what we know, based on what the measurement outcome, you can decide what to measure next. So estimating polyobservables originates from shadow tomography. So which is you have an unknown quantum state rho and you have M observables O1 through OM, and the goal is to estimate trace OI rho, the expectation value of OI within accuracy epsilon. Then estimating polyobservables, which is also referred to as poly shadow tomography, is the special case when the observables are a set of polystrings. Why do we have to estimate polyobservables? The first reason is that it's a key subroutine for variational quantum eigensolver, stabilizer ring entropy, estimation, and so on in quantum experiments. And the second reason is that for distinguishing like pseudo-random state, for learning stabilizer state, from any other learning task, we have to use this as a subroutine. And the third reason here is that it's a test bed for quantum sample memory trade-off, statistical quantum advantage. And also, it can be performed on near-term devices. So this is figures from the recent results on Ribert atom, where they can perform Pauli observables estimation. There are some previous results for learning Pauli observables with and without quantum memory. According to CCHL 2021, the sample complexity of estimating all 4 to the n Pauli observables is 2 to the n over epsilon squared with unentangled measurements. This can be achieved by you divide 4 to the n Pauli observables into 2 to the n commuting Pauli families. And this is also the lower bound. And suppose we have 2 copy measurements, then you can measure all these Pauli strings in n over epsilon to the 4 2 copy measurements, but only the absolute value. And then suppose you have even stronger n over epsilon square copy measurement, then you can further estimate the signs according to HKP21. And finally, we already know a quantum memory samples trade-off, 2 to the n minus k over 3. Suppose we have k qubits of quantum memory. This actually raised several open questions. The first one is that for 2 copy measurements, we can only measure the absolute values trace p rho. This is because we can measure the two-fold Pauli observables, which commute with each other for all the Pauli strings. And by measuring p tensor p, we can get trace p rho square, and that's why we can only estimate absolute value. So a natural question is, can we learn signs using single copy or 2 copy measurements? A second question is that this theorem holds for all the Pauli strings. So can we derive some instance optimal bound? For example, we have a subset of Pauli strings, or we have restricted measurements, not restricted like single copy or 2 copy, but like a subset of single copy measurements. A third question is like, for 2 copy measurements, we have 1 over epsilon to the 4 dependence here. So what is the optimal epsilon dependence? Can we achieve epsilon to the square? And the last question is here, the trade-off is not tight. Notice that for at k equals to 0, this is a lower bound of 2 to the n over 3. But we already know that at k equals to 0, the tight lower bound is 2 to the n. So what is the optimal trade-off here? Let's start with the first question, how to learn signs. We show here that suppose you are given the absolute values, one can estimate the signs of all Pauli observables with like larger than epsilon absolute values using n over epsilon to the 4 single copy measurement. The idea is here. The first step is to estimate the absolute value. We just noticed that p tensor p just commute with each other, so we can simultaneously measure them. And that's how we can estimate trace p rho square, and then we can get the absolute values trace p rho. The second step is to notice that p tensor p acting on rho tensor rho prime equals to trace p rho times trace p rho prime. So suppose we know trace p rho prime, then we can estimate trace p rho. And the third step is just to search for a rho prime with the same absolute value as rho over p, which means that trace p tensor p times rho tensor rho prime is equal to sine trace p rho times trace p rho square. And because rho prime can be like classically searched through brute force, so we can actually achieve this p tensor p and rho prime using single copy POVM. So we can actually achieve this using single copy measurement. And this is a figure illustration. This is rho, and the diagrams here are trace p rho, and we know the absolute value, and we just classically search for a rho prime that has the same absolute value with rho. A second result is the instant optimal bounds. So suppose we have a subset A and we have a set of M denoting a subset of C copy POVMs. We show that the sample complexity of estimating Pauli observables within A is characterized by 1 over delta CMA. Well, the delta CMA is defined to be minimized over all the distributions on A, maximize over all the measurements in M, and suppose the P is choosing according to this distribution, and this chi-square divergence between I plus epsilon p over 2 to the n C copy and C copies of maximum mixed state. Let's briefly talk about how this is proved. So it begins with a distinguishing problem. The first case is that we have a maximum mixed state where trace p rho equals to 0 for all the p. And the second case is you have I plus epsilon p over 2 to the n for random p in A, chosen according to a distribution pi. And in this case, trace p prime rho equals to epsilon times whether p equals to p prime. And suppose we can learn the observables, then we can distinguish between these two cases. And for any adaptive algorithm with t rounds and you can measure C copies in each round, you can describe the protocol as here. So we first perform a C copy POVM in M, and then according to the results, suppose we get S1 and S1 prime, then we go to the second step. Like if suppose we get S1, then we perform M2. Suppose we get S1 prime, then we get M3, and so on. Suppose like we follow this purple line and blah blah blah. So this will result in a tree, in a learning tree of depth T, and average history corresponding to a path. So for 2 cases, we have 2 probability distributions on the leaves of this learning tree. And suppose the protocol can distinguish between these two cases, then the total variation distance between these two distributions is at least some constant, like 1 over 3. And then we can further show that the total variation distance, on the other hand, is t times minimal, is t times maximal in all the measurements, and p is chosen from distribution pi, and the chi-square divergence of c copy in the second case over c copy in the first case. So this just yields what we want in the main theorem. Okay, so then let's do some calculations. Let's do some calculations for some special case. So suppose we have arbitrary single copy POVM, then delta CMA is minimized in the distribution, maximizing single copy measurements, and this psi p psi square average over this distribution. And by the minimax theorem, we can also turn the sequence of min and max, and maximal over all the separable states, two copy states, and minimize in the polystrings in A, and trace this p square sigma. And when A is the set of all xyz strings, then we can explicitly calculate this as 2 over 3 to the n. And when A contains m non-commuting polystrings, this value is 1 over m. And when A contains m commuting families, then this is also 1 over m. And when we can only perform single copy Clifford measurements, then this delta CMA is just the fractional coloring number of the anti-commuting graph of A. So here, anti-commuting graph is we just regard all the polystrings in A as a graph, and if two polystrings anti-commute, then we have an edge between them. Okay, now let's go to the optimal epsilon dependence. Here we show that the sample complexity for estimating all the 4 to the n Pauli observables using C copy measurement is at least 2 to the n over C epsilon square, or e to the minus 6C epsilon over C cube epsilon to the fourth. So when epsilon is smaller than 1 over C and when C is Pauli n, then this means that we either have to suffer from 1 over epsilon to the 4 using entangled measurement, or 2 to the n using unentangled measurement. And this also works for bounded quantum memory case, because every POVM element in bounded quantum memory case can be regarded as a matrix product case with bounded dimension 2 to the k. So the lower bound and also the upper bound here is 2 to the n over epsilon square and 2 to the n minus k over epsilon to the 4. Here we just briefly talk about the proof idea. So we just take the set A as a four set, and the set measurement set M to be C copy POVMs, and the distribution to be uniform. And we just binomial expand the term I plus epsilon P over 2 to the n tensor C. And we just go back to the main theorem. So the value delta CMA can be represented as this. And using Cauchy-Schwarz, we can like decompose it into different terms. Here, the first term just corresponding to the 2 to the n over epsilon squared term. And the second term just give rise to the 1 over epsilon 4 term. Yes, and that's how we derive this lower bound. Okay, as a byproduct of our technique, we can also consider about purity test and purity estimation. For purity test, you are given copies of rho, and the goal is to tell whether it is hard random pure state or maximum mixed state. Here we show that the sample complexity for purity test using k qubits of quantum memory is the minimum in 2 to the n over 2 and 2 to the n minus k. So in the phase transition diagram, it's just like the blue line corresponds to the polystrings. And when we don't have quantum memory, you have exponential sample complexity, and we have n qubits of quantum memory. We have polynomial sample complexity, and this is just a smooth trade-off. But for purity testing, when we have fewer than k equals to n over 2 quantum memory, qubits of quantum memory, then it's flat, which means that the single copy protocol is just optimal. And then when we have more than n over 2 qubits of quantum memory, then we have a trade-off, smooth trade-off. We have a phase transition at n over 2. And regarding the upper bound for this part, we just consider like, suppose we have no quantum memory, then the optimal solution is just to calculate it's just to measurements each single copy in computational basis with some unitary rotation and calculate the collision number, which give you 2 to the n over 2 over epsilon, even for estimating purity. and 1 over epsilon square. And when we have n qubits of quantum memory, you can do swap test. And when we have bounded quantum memory, you can combine a partial swap test and collision number in computational basis in the remaining n minus k qubits, and which give you 2 to the n minus k over epsilon square. So here it's quite interesting. Like, can we get some optimal dependence in epsilon? And here's a following up work on this topic. We show that the sample complexity for purity estimation using k qubits of quantum memory is the median, or like minimizing 2 to the n over k over epsilon square and maximizing 1 over epsilon square and square root over 2 to the n over epsilon. So for upper bound here, it's not square root of epsilon, but epsilon. So here we have a gap. We don't know how to close it. And application for this is distributed inner product estimation, which is proposed by ALL in 2022. In this case, Alice and Bob has rho and sigma, and their goal is to estimate trace rho sigma. So in the original paper, they can only have classical message, but our result can be extended to the case when they have one-way quantum message of k qubits. So when they only have classical message, then the sample complexity is 1 over epsilon square and 2 to the n over 2 over epsilon. And this corresponds to the second term here. And when they have bounded quantum message, one-way quantum message, then this upper bound is 2 to the n minus k over epsilon square, which is corresponding to the first term. And we can also find the phase transition at k equals to n over 2 qubits. And for quantum message smaller than this size, then this has no improvement over classical message. Okay, let's wrap up the talk. The first take-home message is that estimating Pauli observables and purity are test bed for information theoretic quantum advantage, and they have the potential to be performed on near-term devices. The second message is that the chi-square divergence gives the instance optimal bound for estimating Pauli observables. The third message is that the optimal bounds on epsilon dependence is that either you have to suffer from 1 over epsilon to the 4 dependence due to the entangled measurement, or you have to suffer from the exponential scaling in system size using unentangled measurement. And the fourth message is the sample memory trade-off. So we have a smooth trade-off Pauli observables, but phase transitions for purity test. And the later one just indicates that unentangled measurements are optimal when we have fewer than n over 2 qubits of quantum memory. And that's all for my talk. Thank you for listening.